Question 11 says a sine wave is traveling in a string in the positive x direction with speed v. The shape of a part of the string at time t equal to t0 is as shown. The equation of the wave may be given as, and these are the four options. So here we have to write the equation of the wave and whose snapshot at time t equal to t0 is given to us. So from the shape or the graph that's been given to us, we can say that the amplitude is a0. It's very clear. The maximum value of y is a0. And what about lambda, the wavelength? We can see that this distance is 3b minus b or 2b, and that will be lambda by 2. So we have lambda is equal to 4b. Amplitude, of course, is a0, as I said. So these are the two things we have right away. And we can write the equation y at as a function of x and at time t equal to t0, t equal to t0. This equation we can write. We can see that it will be given as a0 cos kx, where k is 2 pi by lambda, the wave number. Because at x equal to 0, we can see that value of a0, it's positive. So this is the equation of the snapshot. Okay. The value of k we have because we have the value of lambda, and k is 2 pi by lambda. So what about the equation of the wave? We note that it is traveling in the positive x direction with speed v. So y as a function, well, y xt, that is what we are supposed to find. And since it is traveling in the positive x direction with speed v, we can say that y xt is same as y. We put t equal to t0, and in time, well, y t equal to t0, and it would have traveled a distance of what? V into t minus t0. That means here we have to put x minus v into t minus t0. This is what we are getting, and now we can write the equation of the wave very easily. We simply have to replace k. In fact, we have to replace x by x minus v into t minus t0 from this equation, and that will give us the equation of the wave. So this is coming out to be a0 cos k. Let's put k as 2 pi by lambda, which is 2 pi by 4b. And as I said, instead of x, we write x minus v into t minus t0. And this, in fact, is the equation of the wave. We can strike this off and simplify this. This will be a0 cos pi by 2b, x minus v into t minus t0. Let's now look at the options, and we can see that, well, option 2 is matching with what we have got. If I just open this bracket, this is what it will come out to be. So that means for question 11, option 2 is the correct option. Let's go to the next problem now. Question 12 says a circular loop of a flexible wire of linear density mu and radius r rotates about an axis passing through its center and perpendicular to its plane in a gravity-free space with angular velocity omega naught. See figure. So we can see that it is rotating in this anti-clockwise sense with angular velocity rather, omega naught. The speed of a transverse pulse moving on the wire in the counterclockwise sense would be, well, so we have a pulse in this wire moving in the counterclockwise sense. We have to find its speed. So we see that the speed of the pulse with respect to the medium, that means with respect to wire itself, is given by the expression, let's call it v1, and this we know that it is under root t by mu. The speed of a transverse pulse in a string or wire, we can use that here, where t is the tension and mu is the linear density. What about tension? If it is rotating with angular velocity omega naught, again we have to apply the concepts of dynamics of circular motion. We can in fact take a small segment and which subtends angle, let's say d theta at the center, and for this segment the forces will be T and T, that means tension at these 2 points. It's a infinitesimally small segment. So the force towards center will provide the centripetal force for this element, and that force is 2t sine d theta by 2. Because if I take this angle bisector, each of these angle is d theta by 2, and the component of t, if towards center, will be t sine d theta by 2. Total force towards center will be 2t sine d theta by 2, and this is equal to dm, and dm itself will be, well, linear density mu into r d theta. R d theta is the length of the element, that multiplied by linear density mu is the mass into omega square into r. So we have r square here then, and we can replace sine d theta by 2 by d theta by 2, and if we do that we have T equal to mu r square omega square. That is the tension in the wire. So the speed with respect to the medium, that means with respect to the wire of the pulse, is going to be under root of mu r square omega square, rather it's omega naught, so it's omega naught square. We can put omega naught here. So this is mu r square omega naught square divided by mu. So we can see that the mu will cancel and we have r square omega naught square, or simply omega naught r. But this is the speed of the pulse with respect to the wire itself, and any point of wire will have speed of omega naught into r. So if the pulse is going in the counterclockwise sense, with respect to the center, its speed will become plus omega naught r, and that means it is equal to 2 times omega naught r. And if we look at the options, we see that it is matching with the first option. So option 1 is correct for question 12. Let's now go to the next problem. Question 3 says a uniform string of mass m and length L is suspended vertically from one end from a rigid support. A short wave pulse is introduced at its lowest end. As the pulse moves up the string, options are its speed is constant, speed increases and acceleration decreases. Both speed and acceleration increase, and option 4 says speed increases and acceleration is constant. Okay, so analyze this situation. We just take a heavy string, uniform string, something like this, let's say, whose mass is m and length is L, and to find the speed of the pulse at any point, let's say at distance x from the lowest end, because as the pulse moves up the string, so we take x as the distance of an element from the lowest end of the string, and we find tension at distance x. So tension as a function of x we can easily find, and that is in fact equal to weight of x length of the string, and that weight will be, we can apply the unitary method, m by L into x is the mass into g. So this is the tension for x length, in fact at distance x from the lowest end, and so the speed, expression for speed is under root T by mu, so it is mxg by L into mu, and the value of mu is m by L. So we see that m and L, they get cancelled, and the expression is simply root gx. And as the pulse is going up, x is increasing, so speed is increasing. So that is one part. What about the acceleration? To find the acceleration, we simply differentiate this with respect to time, and we get a is equal to dv by dt, and that will be equal to under root g. Derivative of root x with respect to t is 1 by 2 root x dx by dt, and dx by dt is nothing but the speed of wave, which we saw is root gx. So acceleration a, we can see that is a constant. In fact, it is g by 2. We are finding that acceleration of this pulse is coming out to be equal to g by 2, and this is a constant. So as the pulse is going up, the speed is increasing, but acceleration is constant. And among the options, option 4 says speed increases and acceleration is constant. It is matching with what we got. So option 4 is correct. Let's go to question 14 now. Question 14 says a progressive wave moving along x-axis is represented by y equal to a sine 2 pi by lambda Vt minus x. The wavelength at which wave speed is half of the maximum particle speed is. Okay, so we can see that the speed of wave is v from this equation, Vt minus x, that term is there. So speed of wave is v, and particle velocity, let's call it Vp. Particle velocity Vp we can get by differentiating y respect to t. So del y by del t, in fact we take partial derivative, and this is equal to a into, well, 2 pi v by lambda, the coefficient of t in this term, into cos 2 pi by lambda into Vt minus x. This in fact is the expression for particle velocity, and maximum particle velocity, for considering maximum particle velocity or maximum particle speed, we can take this term as 1. So Vp max is 2 pi AV by lambda. So we have Vp max, maximum particle speed, as 2 pi Va by lambda. This is the maximum particle speed, and the question says the wavelength at which wave speed is half of the maximum particle speed. So that means half of this. So in the next equation we can write half of this, which means pi Va by lambda is equal to V, wave speed, and this in fact tells us that lambda will be in that case pi A, and which in fact is matching with option 2. So option 2 is correct for question 14. Let's now go to the next question. Question 15 says a bat moving at speed v towards a wall sends a sound signal of 4000 Hz towards it. On reflection, it hears a sound of frequency 4250 Hz. The value of speed v is, and speed of sound is given as 330 meter per second. Well, the question is from the topic waves, and in fact it's based on Doppler effect. So let's write the expression for the frequency heard by the bat. So first of all, we note that it's the bat is acting like a source, and we have a wall here. So in the first instance, well, wall acts as an observer. So the frequency heard by the wall, let's call it F1, is the frequency emitted, which is in fact 4000 Hz. Let's call it F0 right now. So F1 is F0, and it's a case of source moving and the observer wall being stationary. So we have C divided by C minus the speed of the source, which is V, and this is the frequency reflected by the wall, but the frequency that the bat will hear, because again it's moving, so that frequency will be F1, the frequency emitted by the wall, into C plus V, because now the observer is moving towards the source, divided by C. Well, in the expression, C is the speed of wave, that is 330 meter per second, and V is what we are trying to find. So that means we get the equation F2 is 4250 Hertz. So 4250 is equal to F1, which is F0 C by C minus V. We can in fact simplify this here. So this is F0 C by C minus V into C plus V by C, and well, this is the one. F0 is 4000 Hertz and F2 is 4250 Hertz. So we have 4250 is equal to 4000 into C plus V, which we can put as 330 plus V divided by 330 minus V. And let's now simplify this. So we have, well, 1 0 going off here. We have 425 divided by 400 is equal to 330 plus V divided by 330 minus V, and let's divide the numerator and the denominator by 25. If I divide numerator by 25, I get it as 1, and then 175, that means 17, and here it is 16. So well, it's now a simple matter of solving for V. If we solve for V, we find that the value of V is coming out to be equal to 10 meter per second. So for question 15, the correct option is 2. Let's now go to the next problem.